So, what if I told you that our entire universe, everything from the way an electron spins to the massive cosmic web of galaxies, what if it wasn't born from some singular bang, but is actually being computed, right now, from a single line of code? It sounds like science fiction, I know. But today, we're diving into a fascinating idea that proposes exactly that, a grand equation for our very own bounded fractal reality.
And this is it. This little thing is the proposed engine of everything. It's what's called an iterative equation. And all that means is you take the output, z, and you just plug it right back in as the next input, again and again and again. That c you see there, that's a constant. It's a single fixed number that defines the whole system. The rule is just so simple. Take a number, square it, and add this constant. That's the whole game.
And right there, that is the huge, profound question we're going to tackle. Is it possible that a process this simple could generate the, infinite complexity we see all around us? Could our reality just be the result of one number being looped through this simple equation forever? Okay, so how on earth can something so basic create everything? Well, the answer comes from this beautiful, almost counterintuitive field of mathematics. We're talking about the mathematics of controlled chaos, and that idea right there, that's the key that unlocks this whole thing. You see, there's a magic ingredient here, a really simple boundary. The value of z absolutely must stay less than 2. You could almost think of it like a leash on infinity. As long as the number stays inside that limit, the system can get wild, chaotic, infinitely detailed, but it stays stable. It won't just explode and fly apart. And this creates a sort of pocket of controlled unpredictability, which, you gotta admit, sounds like the perfect condition for a stable, interesting universe to actually exist.
Now here's a super important point we need to get straight. The famous Mandelbrot set, that beautiful, trippy image you've probably seen, that isn't the universe itself. No. Think of it as the map of every possible universe that could be stable under this rule. Each and every point on that map is a different value for c. Our specific reality, or so this theory proposes, is something called a Julia set. That's the incredibly intricate fractal pattern you get when you pick just one specific c from that map and let the equation run. So we're not living in the whole map, we're living inside one specific instance.
So, if our universe is one specific Julia set, that brings up a monster of a question. What number defines it? What is our universe's special value for c? Well, the theory gives an answer that is, honestly, just astonishing. It says that number is built from the two deepest, most mysterious constants in all of physics.
First up, we've got alpha, the fine structure constant. This little number, about 1/137, basically dictates how strongly particles feel the electromagnetic force. It's the reason atoms can hold themselves together. And get this, physicists have measured it with unbelievable precision, but nobody has a clue why it has that specific value. The great Richard Feynman himself called it one of the greatest damn mysteries of physics.
And for number 2, we have the impedance of free space. Okay, this one sounds a bit technical, but it basically describes the resistance of the vacuum itself to the flow of energy, like a beam of light. It tells us that even so-called empty space has this fundamental property that shapes exactly how reality unfolds within it. And here it is. This is the central claim of the whole idea. The constant c that defines our reality is what's called a complex number, meaning it has a real part and an imaginary part. And this theory proposes that the real part comes from alpha, our constant of interaction, through some function g. And the imaginary part? That comes from z0, the constant of energy flow, through another function h. Let's just break that down for a second. The real part, the one from alpha, that governs the structure and the strength of interactions, how things stick together. The imaginary part, the one from z0, that governs the flow, how energy actually moves through space-time. And all of a sudden, these two totally mysterious numbers from physics aren't separate anymore. They're two sides of the same coin, the literal code that defines our specific Julia set universe.
All right, this is where it gets really, really exciting. Because if a framework like this is correct, it shouldn't just be some elegant idea, right? It should actually solve problems. And this one claims to solve some of the absolute biggest head-scratchers in all of physics.
So first on the list, the arrow of time. The fundamental laws of physics we have, they work just fine forwards or backwards. So why can we all remember yesterday but not tomorrow? Why do eggs break but never ever unbreak?
Well, the answer, in this model, is purely geometric. Time is just the iteration count, that little n. Every single tick of the clock is one step forward. Zn becomes z to the n plus 1. And you just can't reverse it, because for any given output, there are actually two possible inputs that could have made it. The path forward is unique, but the path backward is totally ambiguous. The arrow of time is baked right into the process itself. What about this one? The hierarchy problem. Why in the world does a single top quark have over 300,000 times the mass of an electron? Our best theory, the Standard Model, it just plugs these numbers in. It doesn't explain them at all. This theory suggests something radical. It says the different particles aren't actually different things, but different behaviors happening inside the same system. Stable, simple orbits within this Julia set, those correspond to light particles, like electrons. But more complex, high-period orbits, those correspond to much heavier particles. The whole hierarchy of masses isn't some random accident. It's a direct result of the geometry of our reality's code. And then we have the big one, the cosmological constant problem. Our best theories predict that the energy of empty space should be 120 orders of magnitude larger than what we actually see. It's so wrong, it's been called the worst prediction in the entire history of physics. But in this model, the solution is just geometric stability. Remember that boundary condition from the beginning, that rule where z has to stay less than 2? Well, for that to actually happen, the universe needs a near-perfect balance of energy. That teeny-tiny non-zero vacuum energy we observe, it isn't some mistake, it's the exact amount of energy required by the geometry to keep our entire reality stable and stop it from flying apart.
Now look, I know this all sounds incredible, maybe a little too incredible. But what separates real science from just cool philosophy is testability. And unlike a lot of other grand theories out there, this one actually makes concrete predictions that we can go out and test.
And that's the crucial part. This isn't just a neat story. It's a hypothesis that can be proven wrong. And that's what makes it science.
So how would we even go about testing it? Well, we could search for faint fractal patterns in the leftover radiation from the Big Bang. We could perform even more ridiculously precise measurements of alpha and z0 to see if they fit the relationship this theory demands. We could even try to map the calculated orbits of this specific Julia set to the known ratios of particle masses. These are real experiments that can actually be done.
This whole idea leads us back to a famous phrase from the physicist John Archibald Wheeler, it from bit. The core idea is that every particle, every force field, every physical thing ultimately gets its existence from bits, from pure information, from the answers to simple yes or no questions. And that really is the final mind-bending thought I want to leave you with. If this theory has even a shred of truth to it, it suggests that our reality is, at its most fundamental level, computational, that we are not living in a universe of matter and energy, but a universe made of pure information, unfolding step by step, iteration by iteration, all according to a single, incredibly elegant line of code.